So let's get started. All right, guys. Thanks for joining again. We are back. Sorry for the delay. I had outage on top of outage for the last 2 or 3 weeks. But that architectural issue is fixed. So we're gonna go ahead and jump back into our CCNA journey. We are still in section 3, which is implementing VLANs and STP, right? We have now moved on from chapter 8 to chapter 9, right? Chapter 9, labeled titled Spanning Tree Protocol Concepts. Okay. All right. So chapter what it covers, if you guys are looking at the objectives, 2.0 network access, 2.4 configure and verify layer 2 and layer 3 ether channel LACP protocol. Okay. 2.5 interpret basic operations of rapid PVST plus spanning tree protocol. 2.5a, root port, root bridge, primary, secondary, and other port names. We're also going to go over 2.5 dot B, port states and roles, 2.5 dot C, port fast, and also 2.5 dot D, root guard, loop guard, BPDU filter, and BPDU guard. We're going to mix this up a little bit, right? Because this is a lot of information. So we may go over a theory, okay? And then the next session may be us hopping into class. This is what we may do, and we're going to have to do because it's just a lot of information, okay? And I want to make sure you guys get it. It makes sense, and if it doesn't make sense, you let me know, okay? So spanning tree, right? Let's talk about it, right? So without spanning tree in general, right? And I'm going to go into detail later. Without spanning tree or a mechanism like that, right? A regular broadcast domain, right? A local area network with redundant links, okay? We would have an infinite we would have an infinite period of frames that are passing from people's PC into the switches that are then looping, right? From switch to switch to switch to switch on those redundant links, right? And if we have loops, then what do we have? We have a broadcaster, right? That is a scenario without spanning tree, right? Of course, in modern age with spanning tree, what the switches do to prevent those loops from happening or those broadcast storms from happening, what spanning tree would do will go ahead and block the ports on the redundant links so that that port would not forward frames, right? We want to, the goal here, right, with spanning tree is to make sure there is one flow of traffic, right, to the root, all right? So two things, right? There's two goals whenever spanning tree does its algorithm, right? And it starts doing its, it starts doing its job, right? From the control plane, right? The control plane says, perfect. All the devices in a VLAN can send frames to other devices, right? In other words, STP or RSTP does not block too many ports, cutting off some parts of the local area network from other parts, okay? All right. So the switch is not going to go ahead and say, hey, I implemented spanning tree. I'm going to cut off all ports. No. Understand the condition with spanning tree, right? Of what it does. For redundant links, it is going to go ahead and block ports. So there is only one flow of traffic, right? Okay. Number two, right? The second goal, frames have a short life and do not loop around the network indefinitely with spanning tree enabled. Okay. If we have spanning tree enabled, that frame, that maybe that broadcast that's leaving your PC, it's not going to go throughout the network forever with spanning tree enabled, right? It's going to be broadcasted. If it's no responses, right? Boom, that frame, it has a lifespan, right? I'm sure you guys heard the term time to live, TTL. When that dies out, the frame dies. Okay, so this chapter is going to go ahead and go into detail about both STP and RSTP, right? So whenever in this section you hear me guys talk, you hear me talking, if I say STP or RSTP, I'm talking about the same thing. In chapter 10, it goes more into detail about RSTP. Okay, but just for if you guys hear me say it, I'm gonna say spanning tree and say STP. All right. Okay. So let's reiterate, right? If we have spanning tree enabled, right, it's gonna go ahead and prevent looping frames by adding an additional check on each interface before a switch uses it to send or receive user traffic, right? Let me get my pencil. Okay, there we go, right? So we have a frame coming from Bob's PC. It gets onto the switch, right? What is the check that the switch is going to do, right? The check that the switch is going to do from the control plane is going to say this, right? If the port is in a forwarding state, right? In that VLAN, use it as normal, right? If that port is in a blocking state, however, block all the user traffic, right? And do not send or receive any user traffic on that interface for that VLAN, okay? So remember, before the switch does anything, right? Before it forwards out any frames, it checks its interface, right? Because again, all this is software, right? All this is being done by the control plane, right? Telling the software, hey, and when I say control plane, I mean the CPU. The control plane says, hey, based on what I see here in software, here's what I don't want you to send out, or here's where I do want you to send out that. So Bob sends the frame to the switch, right? Switch 3 says, hey, this is in a forwarding state. This is in a forwarding state. Forward that traffic out. Okay. What does switch 2 do? It does that same check. Is the port in a forwarding state or is it in a blocking state? As you can see by this diagram, it's in a forwarding state. We're going to go ahead, send that traffic out, all ports. Why? Because it is in a forwarding state. What about switch 1? You guessed it, right? It's in a forwarding state for both ports. What's happening? What is actually happening? We have packets leaving. I'm sorry, packets is layer 3. Layer 2, we have frames leaving switch 3 going to switch 2, right? Then they're leaving switch 2, right? And they're going to switch 1. Then they're leaving switch 1, they're going to switch 3 and switch 2, right? Switch 2 is also sending it back to switch 3. Guys, we have a broadcast storm, okay? This is what it looks like when spanning tree is not implemented, okay? If you guys can imagine, if we have this, right? If you guys have this in your normal businesses, no work would get done. The internet probably wouldn't even exist. Okay. So that is a key part that I want you guys to understand. Before any frames are sent out on the wire, the switch is going to say, hey, is this port in a forwarding state or is it in a blocking state? Okay. All right. Let's keep going. All right. So we've covered the need for spanning tree, why we need it, or what have you. We talked about having his broadcast storm, what have you, right? But what essentially happens, right, whenever that broadcast storm exists, right? Well, what we're going to have is what they call back table instability. Okay. So what that means, right, is we went ahead and let me get my pencil again. The frame originated at Bob's PC. Okay. That frame, right, entered switch 3. So switch 3's MAC address table said, hey, for this MAC address, map it to port fast Ethernet 0/13. Okay? So my Kivia, so if this frame leaves switch 2, right? It leaves switch 2 and it also forwards this frame out. to switch 1. Okay? So then, Donovan, right, it goes ahead and does the same thing, right, to switch 2 to switch 1, right? Now, that frame is going to come from switch 2 and switch 1, right? Because now the source and destination, right, of the frame has changed. So now what switch 3 is going to say is it's going to see that frame and say, "Hey, I had an entry in my MAC address table for this frame being received on this interface. But I'm going to go ahead and put an entry on gigabit 0/1 as well." Uh-oh. Now the broadcast storm has created MAC table instability because now I don't know where to map that Bob's MAC address to. Okay. All right. So one of the three major functions of the switch that you guys learned about is switches flood frames sent to unknown unicast MAC addresses, right? So if Bob is trying to send a frame to a PC that's maybe not on the network, what's going to happen is that destination, right? The destination MAC address is going to be set to broadcast, right? If we didn't have spanning tree, that is exactly what would happen. Is a broadcast storm. Okay, let's go over the actual definition of all three. Okay, all right, and this is a key topic, so guys take screenshots and take notes. Okay, so table 9-2, three classes of problems caused by not using spanning tree in redundant local area networks. Okay, broadcast storms. It is described as the forwarding of a frame repeatedly on the same links, consuming significant parts of the link's capacities. Okay, MAC table instability, the continual updating of a switch's MAC address table with incorrect entries in reaction to looping frames, resulting in frames being sent to wrong locations. Okay, it's something that we didn't went ahead and touch on, which is multiple frame transmission, a side effect of looping frames in which multiple copies of one frame are delivered to the intended host, confusing the host. Okay, all right. So we didn't touch on that, but I'll go ahead and touch on um, MFT. Okay, so multiple frame transmission, right? Let's say we do have a destination for our frame, right? Okay, so we have our source, and our destination is Archie. Okay, so we have Archie's destination, right? We go ahead, we said, all right, we know where to send it. Switch 3 says, hey, I'm going to go ahead and send it here. I'm going to go ahead and send it here, right? What's switch 1 going to do? I'm going to go ahead and send it here. I'm going to go ahead and send it here. I'm going to go ahead and send it here, and so on, right? So switch 3 may receive the frames, right? And say, hey, here, Archie, right? But then the switch 2 is also going to receive frames from switch 1 along with switch 3. So now, along with that MAC table instability, whenever Archie tries to reply back to Bob, switch 2 doesn't know, hey, I don't know where to send this, right? So I can't transmit this data. Okay? All right? So that is the theory of multiple frame transmission, right? It's going to confuse the host, right? It's going to confuse Archie's PC, but also it's going to confuse the switch. Okay? Does that make sense, guys? Okay, awesome. All right. So what does spanning tree actually do? Right? So spanning tree prevents loops by placing each switch port in either two states, either a forwarding state or a blocking state. Real simple. Okay? If you see switches, they're connected to each other. They're either in a forwarding state or they're in a blocking state. Right? If there's an interface on a switch, um, and it's in a forwarding state, it's going to act as normal. Right? It's going to be able to transmit and receive frames. Okay? Real simple, right? Now, if a interface is in a blocking state, me get my pencil, right? Like gigabit 0/2, right? On switch 3, okay? Just like you guys learned in the previous section, right? The interface does not process any frames except for spanning tree messages, okay? And some other control plane stuff like DTP and all that stuff that you guys learned. But as far as actual traffic, it will not process it. It will not receive or transmit. Okay? But essentially, right, this is what is happening, right? So now let's take a look at this diagram with spanning tree enabled, right? So step one, we got Bob sending that frame to switch 3, right? And this is with a spanning tree enabled, right? What's going to happen, right, is we're going to have that check again. Hey, which interfaces are in a forwarding state, which interfaces are in a blocking state. Switch 3, right, is going to go. It's going to go ahead and do what we call index, right? It's going to go with the lowest interface first. It's going to say, hey, right, gigabit 0/1. Hey, you're in a forwarding state. Gigabit 0/2. You are in a blocking state, so I can't forward any frame, right? So I'm going to go ahead and only be able to forward that frame out of gigabit 0/1. Okay. Step 3. Switch 1 is then going to go ahead and flood the frame, right? And since the destination is unknown, right, it's going to flood it out of all of its ports except for the port that it received the frame on. Okay. So it received the frame on gigabit 0/2, right? It's not going to forward it outside of that, right? It's going to forward it to gigabit 0/1, right? So then we go ahead and move on to step 4, right? Step 4 is going to go ahead and say, hey, right, I'm going to go ahead and forward that, flood that frame out of fast Ethernet 0/12, right? And out of gigabit 0/1, right? See, guys, on switch 3 side, okay, that interface is blocked, but not on switch 2 side. And we'll learn about that in the future, right? But switch 2 and switch 1 are still doing those checks of, hey, which ports are in a forwarding state, which ports are in a blocking state. Okay? All right. So this is what it looks like, right, in regards to an active spanning tree topology. Okay? Right? Going from what we had before to what we have now, you can go ahead and call this STP convergence. Okay? That refers to the process by which switches collectively realize that something has changed in the LAN topology and determine where they need to change which ports block and which ports forward, right? We had spanning tree. We didn't have spanning tree in our last diagram. Now we do. The spanning tree algorithm said, hey, we need to block on gigabit 0/2 off of switch 3. Excellent, right? Now spanning tree convergence has happened. You guys will need to know that for the exam. Okay? All right. That. Okay. With that being said, I'm going to stop here as an intro. Come Sunday, we're going to jump into how spanning tree actually works in detail. Before I close out, any questions?
No, not for me.
Okay. All right.
Not done for me either.
Okay. All right, guys. Well, I'll go ahead and close it here. I will see you guys Sunday.
Alrighty, thanks. Bye, guys.
All right,
All right.
thanks. Bye, guys.